Let's start Notes 13.2 covering geometric power series and their convergence test by doing a little bit of an Algebra 2 review. This little exclamation point in mathematics is a factorial. Factorial, such as 2 factorial, is just a multiplication problem where we start at 1 times 2 and get 2. And that pattern continues with 3 factorial. It will be 1 times 2 times 3, which of course would be 6. 4 factorial would be 1 times 2 times 3 times 4, or 24. Also, when we have a sequence is just an ordered pair, or not an ordered pair, excuse me, an ordered list of numbers. And when we have an odd sequence would be set up like this: 2 times n plus 1, where we can start at n equals 0 and then go to infinity or anywhere in between. But an infinite sequence would be n equals 0, we'd get 1, n equals 1, we'd get 2 times 1, which would be 2, plus 1, which would give us 3. So you can see that this is always going to give us an odd number, and the next n would give you the next odd number in this sequence. If you're looking for even numbers, then it would be 2n. From n equals 0 to infinity would be an infinite sequence. Again, you can see the pattern here. 2 times 0 would be 0, 2 times 1 would be 2, 2 times 2 would be 4, and then of course 6, 8, and so on. The term series is based upon a sequence. It's all of those numbers in the sequence added together. So therefore, a series is just a sum of a sequence. Let's review what we did in our previous lesson, and that was our nth term test. The nth term test are sometimes called the divergence test. Divergence is called that because it basically will tell us if something diverges or not. And the way that's determined is, first of all, the nth term has to absolutely approach 0. So it must approach 0, or if not, then the series will diverge. So we take the limit as n goes to infinity of the terms, and we see that the nth term is not equal to 0, then we know for sure that that series diverges. If we do this analysis and we see that the nth term is approaching 0, then this series might converge, but again it might also diverge. We have to do more tests in order to find out. Next test we had was when we looked at the terms and we found out that we had a geometric series. What determines a geometric series? Well, a geometric series is any series that has a common multiple between each term, or a common ratio. In other words, if we go from 2 to 4 to 8 to 16, that common multiple is 2. Standard form of a geometric series would be the nth term is always equal to the first term times that common multiple or ratio to the n minus 1 power. That gives you the term, therefore the series would be the sum of those, so that would give us a sum from n equals 1 to infinity of each one of these terms, t sub 1 times that common ratio to the n minus 1 power. It's not always written like that. Sometimes we take this from n equals 0 and go to infinity. It still is the first term times that common ratio, but that common ratio is now just raised to the nth power. Each one of these terms could be integers, but they also could be variables like we did in our previous lesson. Regardless of what that is, if we find that we have a geometric series, then it will always converge to this value, the first term divided by 1 minus the common ratio, and that is only if the absolute value of r is less than 1. If that common ratio, r, the absolute value of that is greater than or equal to 1, then that geometric series will always diverge. In order for a series to converge, or in order for the series to have a sum, the nth term must always go to 0, and it actually needs to go there rapidly, as we talked about in our previous units about convergence and diverging functions. Getting down to 0 rapidly determines whether something converges or not. A power series can converge for all values of x if we do an analysis on them and we find out that that series does converge. Okay? But sometimes when we do an analysis on it, we say, wait a second here, this will only converge if x equals a certain value. So sometimes we may do our analysis and we'll find out that only in one special case, when x equals, say, 7, that the series converges. Sometimes we will find out that there's an interval of numbers or values for x that will work. It could be an open interval or it could be a closed interval. And then sometimes, of course, we'll find that it never converges. In other words, there's no value of x that will allow the series to converge. In other words, they diverge. So when we do our analysis and we're saying, does a certain series converge, to summarize this again, I could find out that, yep, it converges no matter what I choose for x, it always does. I could find out that, yep, it does converge, but only when x equals one single value, or only when x is between a range of values. Or I'll find out, nope, it doesn't converge, it diverges. It's going to be one of these four, no matter what. For all values of x, a single value, a range of values, or no values. The set of values for x, in which the series converges, is called the interval of convergence. And again, that interval could be all values of x, a single value of x, a range of values of x, or no values of x. Okay? And currently, we're not going to stress about the endpoints for that. The distance from the midpoint of that interval to the endpoint is called the radius of convergence. So two terms that you'll be needing to understand, because they'll be asking you find the radius of convergence or find the interval of convergence. So let's do a quick example to make sure we understand these terms. Okay? So when I look at this, I can see that my first term is this guy right here. That term, t sub 1, is just x minus 6 divided by 2. And then when I look at the next term, I see that, yep, that's that same term, but it's squared, and then that same term that's cubed, which tells me that not only is this the first term, but this is the common ratio, x minus 6 divided by 2. So what I want to do is I want to look at this, and I know that this will converge. This series will converge, as we've said, or I'm sorry, let me go back and quickly remind you that this is a geometric series because they told us it was. If they didn't say it was, we can see that there's a common ratio between each one of these terms in this pattern, and that's this common ratio. Okay? So in that case, or because we have a geometric series, we're going to evaluate this common ratio and make sure that it is less than 1. In other words, we're solving this kind of Algebra 1 problem of solve this inequality. Then we know with this we would multiply both sides by 2, and we would have this. X minus 6 is less than 2. This value here is our radius of convergence. Because think about this. On a number line, we know that this absolute value would be at 6, or this absolute value inequality would be centered at 6, and the values that would make this true would be 2 to the right and 2 to the left of this. In other words, this would be from 4 to 8. And remember how we solved these in Algebra 1? We set these up by putting it as this type of inequality where we know that x minus 6 has to be between -2 and 2. Add 6 to this, and this would be a positive 4 is less than x, which is less than 8. So from this algebra analysis, we know again that our radius of convergence or I guess I could say R equals 2. The interval of convergence is the inequality that we have here. 4 is less than x, which is less than 8. Okay? Interval of convergence. Remember yesterday, or in the previous lesson, we talked about this interval of convergence also being the domain, so that can be used interchangeably. The domain of this, in order for this to converge, would have to have x values between 4 and 8. Okay? So also you kind of see why these terms are used. You can see that we are centered here at 6, and our radius of convergence would be 2 this way and 2 that way, and our interval of convergence is between 4 and 8. That's an interval. Sometimes we might do an analysis here, and we might find out that our radius equals 0. If the radius equals 0, then that's a case where the radius, the series converges for one single value of x. That was this one right here. Okay? When we get r equal to 0, then there's only one single value of x that will work for that series to converge. Sometimes we'll evaluate this and we'll see that the radius is infinite. In that case, all values of x will allow the power series to converge. In other words, that's this example, or this one here. When our r equals infinity, then all values of x are used, or can be used, and it will and the series will converge. Our example number 5, we had this range of values, and that's in this case here when r doesn't equal 0 and it doesn't equal infinity, we have r equals some real number where that real number is not equal to 0. Then you're going to have some interval of values that it will work. Let's talk about this term power series and what it means. A power series is a polynomial which has x as its variable, and it's going to be of some form that looks like this. A sub 0, that first term, plus a sub 1, sorry, that should be a 1, times x, plus a sub 2 times x squared, plus a sub 3 times x cubed. And you can see that we have this pattern, a sub n minus 1, x to the n minus 1, plus then a sub n times x to the n. So that is a polynomial expression that we could also write as the sum as I goes from 0 to n of a sub I times x to the I power. So this is a power series where the coefficient a sub I are all going to be real numbers and n is a natural number. Of course, the natural numbers in this case would be or whole number, I guess I should say here, because in this case I did start at 0. So the whole numbers from 0 to whatever n is. The degree of the polynomial is the highest k value for which x of k appears with non-zero coefficients. So in these examples below, let's determine the degree of each one of these polynomials and state why it's not a polynomial. You can see from this one, we have a degree of 3, a degree of 2. The degree of 3 is the highest, so this is a polynomial of degree 3. Next one, degree of 0, 1, 3, 5, 7. 7 is the highest of each one of these terms, so this has a degree of 7. Next one, you'll see that we have a negative 1, 3, and negative 5. Unfortunately, when we talk about the degrees of our polynomials, we don't consider these negative exponents as the degree. So this is not a polynomial, because if it were a polynomial, all of the exponents would be whole numbers. In this case, we have a negative power. So we can just say, hey, I see negative exponents, therefore we don't have a polynomial. The next one, you can see we have 2, 4, and 6, but we have that x squared times a sine, a cosine, and a sine, and that is going to cause this not to be a polynomial. In a polynomial, the function can only be powers of x. In this case, since sine of x and cosine of x are not powers of x. So you can see here, I'll read this statement. The point is that a polynomial has a constant term which may be 0 and a finite number of terms with positive exponents for x. And all of those must be whole numbers when we look at their coefficients. So a power series in the variable x will always represent a polynomial except that it contains an infinitely many powers. Okay? So this is a polynomial of degree n. When we take that and go to infinity, then we have what's called a power series. Remember what we talked about in our previous lesson. Series are, by the term series, infinite. So let's define a power series. A power series centered at x equals 0 is a polynomial that has infinite many terms, and it's going to look like this. A sub 0 plus a sub 1 times x plus a sub 2 times x squared plus a sub n minus 1 times x to the n minus 1 plus a sub n to the x, or times x to the n plus, and then I'm going to put my dot, dot, dot here because this is going to go on forever and ever. Or we can write it in summation form. I equals 0, the sum from I equals 0 to infinity of the coefficient a sub I times x to the power of I. A sub I represents the coefficient of the nth term. A sub n is independent of x and may be expressed as a function of n. So here's an example of a power series, and we'll just say let's this equal f of x. It's going to be some function. So, just a note here, we want to think of these also as a function and a function of x. As x changes, then the value here will change. So if we think of this, let's just go ahead and find f of 2, which will be the sum from n equals 0 to infinity of x to the n, and when x equals 2, this will be a 1 plus 2 squared plus 2 cubed plus forever and ever and ever. It should be pretty obvious to you that this next number is going to be larger than the previous one. As a matter of fact, twice as large. So this will definitely diverge. Again, should be pretty obvious because you can see that value here keeps going on forever and ever and ever and ever. Okay? Therefore, this series does not define a function that can be evaluated at x equals 2. So, what is the value of the function? There is no value. It's going to diverge. Let's do the same thing and evaluate this at x equals 0. We're going to take the sum from n equals 0 to infinity of x to the n, and we're going to substitute in 0 in here. This would be 0 plus 0 squared plus 0 cubed plus, and you'll see this time that we do get 1. Therefore, the function is defined, f of x is defined at x equals 0. This will definitely converge to 0. Pretty simple power series to evaluate. So let's go back and look at our geometric series. We have a geometric series that where each term is t sub n equals t sub 1 times that common ratio to the n minus 1 power. In summation form, we wrote this two ways. We said n equals 0 to infinity of t sub 1 times r to the n, or we wrote it from n equals 1 to infinity of t sub 1 times r to the n minus 1 power. Sorry about getting that off the page. So, if we have a geometric series that looks like this, let's write a formula for that. So, quick analysis, like we've done before, we notice that the first term is 1, and then you can see times x times x times x, but we also go negative, positive, which is telling me that that common ratio has to be a negative value, in this case negative x. So let's check our domain here, and that domain will be a geometric series that converges only when the absolute value of this r is less than 1. In other words, we're trying to find our interval of convergence. That interval of convergence will be, when we evaluate this, the absolute value of negative x is less than 1, which of course will be between negative 1 and 1. That's our interval of convergence. Okay? So we know that since this will converge if x is between those, we can use our formula, first term 1 divided by 1 minus our value of r. In this case, it's a negative x. That is the value, or a formula for this function, whatever our x value is. Okay? In summation form, we could write it like this. The sum from n equals 0 to infinity of first term 1 times negative x to the nth power, which also could be written as the sum from n equals 1 to infinity, and I won't use the 1 in there, I don't have to, of negative x to the n minus 1. Either way that could be written. Okay. Next one, it gives us the formula, and it says let's write the geometric power series represented by this. So let's take a look at this. I can see from this that my first term, t sub 1, is 1, because you can see this is of that form. Sneak it in down here. T sub 1 equals 1 minus our common ratio. From here, t sub 1 is that guy right there. And then, looking at this, it's subtracting 2x, so that's going to be our r value. Our r value is going to be 2x. Now we do need to check our domain here and find our interval of convergence. So the domain here will only converge when this is less than 1. Divide both sides by 2, and this will give us x. The absolute value of x must be less than 1/2. That again is our interval of convergence. So let's write our formula for this. This, of course, will be the summation from n equals 1 to infinity of our first term, 1, times our common ratio, 2x raised to the n minus 1 power. Which means when we get n equals 1, this will be 2 to the x to the 0 power, or 1, plus 2 minus 1 is 1, 2x, plus, next term, we're going to actually take and put in 3 minus 1 would be 2, so we're going to have to square this and get 4x squared, plus then you can kind of see the pattern. I can either multiply each one of these by 2x, or again, I can just substitute in for n and determine what that next term is. And of course, since this is a series, I have to put a plus dot 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 to indicate to the grader that this is going to go on forever and ever and ever. Let's do a couple more examples here of these. So, this function is defined as 1 over 1 minus x. We know from this it matches our form of t sub 1 divided by 1 minus r, that geometric series. It matches that form perfectly for us. So we can quickly look at this and know that t sub 1 equals 1, the very first term. Our common ratio r is equal to x, which means our domain is going to be the absolute value of x is less than 1. And we can just start by writing these terms here. We know that the first term is 1, and then we'll multiply that by x, and then that one by x, and the next one by x. And our general term will be just x to the n. Plus, and again, this is going to go on forever and ever. And we also want to write this in summation form, which would be the sum from n equals 1 to infinity of x to the n minus 1. And this is going to only work on our interval of convergence from -1 to 1. Okay. So, let me explain some of the things that it's asking for or finding. Obviously, this is our first term. This is our common ratio. This is the domain, or it could also be called the interval of convergence. Then, these are all of the terms in the series, or the series itself. This is the series in summation form, and then we clarify it by giving the interval of convergence. So, make sure when you're doing homework or quiz problems or test problems that you address whatever they ask for and put it in a form that they are requesting. The series itself, the general term, the series in summation form, the interval of convergence, and then the specific parts of it, the first term or common ratio or domain. Let's take a look at our next one. Now, you can see from this one that our first term is 1. This time, our common ratio is going to have to be -x, okay? Which means our domain is going to be whenever that r value is less than 1, or the absolute value of -x is less than 1, which is just going to be x is less than 1. Let's start writing these terms. First term is 1 times -x. Multiply that by -x, or the opposite of x, and we get plus x squared minus x cubed plus x to the 4th plus ... Now this is our general term. Our general term will be -1 to the nth power times x to the nth power plus ... And now let's write this in summation form. In summation form, I could write it like this. N equals 1 to infinity of -1 to the n minus 1 times x to the n minus 1. Okay. Now, before you just skip ahead in the video, I want to make sure that you have a good little check in your brain and you say, okay, let me make sure this works. Go ahead and check when n equals 1. I have 1 minus 1, which is 0. Anything to the 0 power is 1. And then 1 minus 1 is 0. Anything to the 0 power is 1, so I have 1 times 1. That matches my first term. Let's check our second term. When n equals 2, this will be 2 minus 1, which will be 1. Negative 1 to the first power is negative 1. 2 minus 1 is 1. X to the first power is 1. Negative 1 times x is negative x. Okay? And again, it's a good little practice whenever you do this, just to make sure, will that match what I have here? And yes, indeed, it does, so I'm confident in my series. Now, one thing we also need to note here is this, of course, will only work for all values of x when we are between negative 1 and 1. Or again, you could write the interval of convergence as the absolute value of x is less than 1. Either one of these are acceptable for that. Okay? Now, I also want to show you that this can be written in different forms. Why is that important? Because you guys know a good portion of your test is multiple choice, and you need to match what they have. So another way of writing this would be the summation from n equals 0 to infinity. Sometimes they like to choose 0, which means that this is going to have to be negative 1 to the n and x to the n. Quick check again. I'm going to start at 0. 0 power is 1. 0 power is 1. 1 times 1 is 1. Next term would be to the when n equals 1. So this would be to the first power. First power, negative 1 times x would be negative x. 2 would be positive 1 times x squared, and that checks again. Also, I could also see this as the summation from n equals 1 to infinity, and I could combine these two together. They're both at the same powers, so this could be written as negative x to the n minus 1 power. Or, of course, the summation from n equals 0 to infinity of negative x to the nth power. Okay? So on a multiple choice, they might put this one as the answer. So don't just lock yourself into saying, okay, this is the only way to write these series. And then, of course, on the homework, as it's been from the very first one, when do I stop? When your answer matches the answer book or the answer key, whatever's provided for you, the answer in the book. Okay? Not just look at their answer and write it down, but manipulate your answer to match theirs. Let's take a look at our next one. Okay? Now, you'll see on this one, this is a variation that I haven't seen before. Remember, I need to have t sub 1 over 1 minus r. 2 is definitely not 1. So I have a problem with this one that I need to solve. This has to be 1, not 2. Okay? So hopefully your fraction skills can come back to you real quickly here, because I need to divide all of this by 2 in order to get this to 1. So of course, when I divide by 2, the numerator becomes 3 halves, and then the denominator, 2 divided by 2 is 1, minus x squared divided by 2. Again, I've got to get it to this form here. This is some number. Don't really care what that is on top, as long as it's some value that's not 0. And then 1 minus r, 1. Now I have 1. Now I know that my first term is going to have to be 3 halves, and the common ratio is going to be x squared divided by 2. So let's check our domain to find our interval of convergence. This will only converge when that common ratio is less than 1, or the absolute value of x squared is less than 2. To get this to an x, I need to square root this, and then to be x, the absolute value of x is less than the square root of 2. Or we can write it as negative square root of 2 is less than x, which is less than the square root of 2. I think we've got our ducks in order now so that we can go ahead and write this expression. We're going to start out with our first term, 3/2, plus our next term will be 3/2 times this, which would give us 3x squared divided by 4, plus, multiply again by x squared divided by 2, 3x to the 4th, and then, that should be an 8, plus, we'll do one more here, 3x, adding our exponents and multiplying, should give us something that looks like that, plus dot, 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 put the dot, dot, dots in between, and this will be the general term. The general term is going to look like this. It has 3/2 times x squared over 2, and this time we'll just put it to the n minus 1 so it kind of matches my summation. So here's my general term, and then writing this as a summation, this will be the sum from n equals 1 to infinity of 3/2 times x squared divided by 2 to the n minus 1. And of course this will be for all values of x between, I'll run out of room, I'll put it as the absolute value of x is less than the square root of 2. So that's our interval of convergence. And just like we did before, I do want to rewrite this in a different way that they may write it. And it could look like this. Let's go from n equals 0 to infinity. And then, of course, this would have to be written as 3/2, and then x squared divided by 2 to the nth power. Now, that may not be the only variation that they have here, because what they may do is do a little manipulation of this back to your early Algebra 2 days with your exponents, and I'll keep this as from 0 to infinity. I could factor out the denominator here. The denominator would be 2 to the nth power. 2 to the nth power times 2 would make this 2 to the n plus 1 as our denominator. Again, Algebra 2 skills. 2 to the n is the denominator, times another 2 would mean this would be 2 to the n plus 1. 3 is going to stay as is. And then a power to a power multiply. This could be written as 2n, x to the 2n. Power to a power, x squared to the nth power would be 2n. And of course, all of these still would be for all values of x between negative square root of 2 and the square root of 2. Let's take a look at another one. You can see again, we have the dilemma of this is not of the form of t sub 1 divided by 1 minus r. So we're going to have to get this to a 1, so let's divide by 3. That will give us 5/3 in the numerator. 3 divided by 3 is 1, and of course x divided by 3 is x over 3. Our first term will be the numerator, 5/3. Our common ratio is going to be x divided by 3. Let's check the domain by doing the absolute value of this guy being less than 1, which means when we multiply by 3, oops, this should be a negative. I see there's a positive in here. This should be a negative and a negative. Doesn't matter in this absolute value, but it will definitely matter when we start writing our terms. Multiplying by 3, that means that the absolute value of x has to be less than 3, whether it's a negative or not, or we have that interval from -3 to +3 that this will converge. Let's write our series out. First term, 5/3 plus 5/3 times this negative x plus 3 will make this negative 5x over 9 plus a 5x squared over 27 minus 5x cubed over 81 plus dot dot dot. We should have 5/3 negative x over 3 to the n minus 1 as our general term. And then we'll put more dot dot dots to get full credit. Then we'll write our summation, n equals 1 to infinity. And we have the pattern of first term times our common ratio to the n minus 1. And this, of course, will be for all values of x between 3, or negative 3 and 3. Let's again practice rewriting this. We should have a summation from n equals 0 to infinity of 5/3 negative x over 3 to the nth power. And then let's manipulate this again. So what would be a way we could put, remember how we did our denominator? The denominator again could be this 3 to the n times 3, or 3 to the n plus 1. And then we could have, I'm going to go ahead and address this negative separately. So this would be 5x to the n, and then I'll multiply all of this by negative 1 to the nth power. That kind of shows that it's going positive, negative, positive, negative. Okay? And of course, this could be rewritten. I'll go ahead and do that too. N equals 1 to infinity. And if I do kind of some of those same things I did here, you'll see that this would be 3 to the n minus 1 times 3. So the denominator is just going to be 3 to the n. Then the numerator would be 5x to the n minus 1, and then negative 1 to the n minus 1. So any one of these forms would be acceptable for this and could be a multiple choice. And just make sure on each one of these I do stipulate that this will only work on this interval of convergence. Let's take a look at the next one. Okay? Now, all of these have been centered at 0. Go back to your Algebra 1, and you know if something's not centered at 0, we have a horizontal shift. We're going either left or right with this. So if we're going to be centered at 1, that means we need to have an x minus 1 in here. You can see we don't show x minus 0, x minus 0, x minus 0, because we are centered at 0 for those. But if we have something that's centered at 1, we're going to need to see it of this form here. So what I'm going to do is use a little algebra on this one and rewrite this as 5 divided by 2 minus x, the quantity of x minus 1. Okay. Did not change this at all. All I did was rewrite it. It's still equivalent. Okay. I took 1 away from here, and you can see when I distribute this, this would be a negative x, this would be a positive 1, and we would still end up with the same thing. Now we're also of the dilemma now that, remember, this has to be 1 minus, so we still need to get rid of that or take care of that by dividing by 2. And this would give us 1, and then minus the quantity of x minus 1 divided by 2, which in this case gives us our first term, 5/2. Our common ratio is going to be the quantity of x minus 1, divided by 2. To check our domain, this common ratio must be less than 1. Do a little bit of algebra on this one, multiplying by 1 the absolute value of the x minus 1 has to be less than 2. And then, of course, we can evaluate it like this. You recall from your Algebra 1 days, we set up this interval, and, oh, I'm not sure why I keep putting a 2 there when it should be a 1. Okay. I need to add 1 in all of these. This, of course, would be a -1, x, and then this becomes 3. This is our interval of convergence. By manipulating this common ratio when we set that inequality less than 1. Now I think we're ready to go. We have our first term, this guy right here, 5/2, plus 5/2 times the quantity of x minus 1 divided by 2, plus 5/2 times the x minus 1 divided by 2 squared, plus dot, dot, dot. I think I'm going to probably go ahead and rewrite this as 5/2 plus 5/4 x minus 1 plus 5, I square this, multiply by 2, 5/8 x minus 1 squared plus 5/16 quantity of x minus 1 cubed, which means our general term could be written in a number of ways. I'll write it back the way we had it in the previous one, with the first term and then our common ratio of x minus 1 over 2 to the n minus 1 power. Put my dot, dot, dots. They're kind of particular. I'll make sure you put the dot, dot, dots in there. And then we'll write this in summation form. The summation from n equals 1 to infinity of 5/2 times the quantity of x minus 1 divided by 2 to the n minus 1 power for all values of x between, this one right here, between -1 and 3. I'll go ahead and rewrite this as, just moving it up here since I ran out of room. I could write it as n equals 0 to infinity of 5/2 times the quantity of x minus 1 over 2 to the nth power. Or being a little creative, I like that denominator, getting that constant out. We could write this as n equals 0 to infinity of 5 over 2 to the n times 2 to the n plus 1 power in our denominator. And then we just say x minus 1 to the nth power. And again, each one of these would still have to be for that interval of convergence. Okay? So hopefully that provided some good information for you to do on our geometric power series and the test of convergence for that. And that's what we concentrated on today, just the geometric power series. Hope you enjoy this, and I'll see you for your next lesson later.